Welcome, curious minds and sleepy thinkers. You've found a soft place to land where the questions are big and the pace is slow enough not to jolt you out of your pillow cocoon. Tonight, we're going to tiptoe into one of the most mysterious questions ever asked. What are these cosmic whispers we call black holes, and what do they truly reveal about the tapestry of our existence? But don't worry, we'll take it slow. This isn't a race through equations. It's more like floating through a galaxy of ideas with a cup of chamomile tea, letting the vastness of the universe gently unfurl before our mind's eye. The universe holds within its vast, silent expanse wonders that stretch the very fabric of our understanding, and among the most profound of these are the black holes. Imagine, if you will, the deepest, darkest corners of a boundless ocean where unseen currents pull everything into their silent embrace. That, in a way, is a black hole, a cosmic maw invisible and ever hungry, lying in wait. They are whispered about in the cosmic winds, known only by the way they twist and tug at the light and dust and stars around them, like a phantom limb, leaving an undeniable imprint on the air. These aren't just objects. They are places where the rules we thought we knew bend and break, where the very concept of time and space becomes a fluid, shimmering thing, warped by an unimaginable force. Think of gravity, that familiar pull that keeps our feet on the ground, and the planets dancing around the sun. Now imagine that pull intensified, magnified beyond anything we can truly conceive, so potent that not even light, the swiftest messenger in the cosmos, can escape its grasp. Once you drift too close, that silent embrace becomes an unbreakable hold, a point of no return from which the journey can only continue inward. They are in every sense gargantuan voids, not empty in the way a forgotten attic might be, but filled with a crushing density that devours all, leaving behind only the ghost of its presence in the swirling chaos of what once was. There's a quiet awe that settles over us when we ponder these cosmic giants. They are terrifying in their power, yes, but also utterly fascinating. It's as if the universe, in its infinite wisdom and playful cruelty, decided to take its fundamental laws, the very bedrock of our reality, and push them to their absolute limits. When such overwhelming power is applied to the very fabric of existence, we are granted fleeting glimpses into the strangest aspects of physics, the kind that gently, persistently, make us question the very nature of our own perceived reality. It's like finding a hidden door in a familiar house, and when you open it, you discover a landscape of impossible beauty and perplexing logic. So as we settle into this quiet exploration, let us allow our minds to wander, to consider, what truly are black holes? What slender threads of knowledge have we managed to gather about them from across the light years? And perhaps most importantly, what profound lessons do these silent cosmic teachers offer us about our own fleeting existence, about the universe we inhabit, and about the mysteries that still lie in wait just beyond the veil of our current understanding? We are not seeking definitive answers, but rather a deeper appreciation for the grand questions themselves, allowing them to wash over us like a gentle wave, calming the mind while subtly awakening the spirit of inquiry. These cosmic entities, so central to our story tonight, begin to unfurl their secrets, not with a bang, but with a whisper, appearing in a startling variety of sizes, almost as if nature itself enjoys experimenting with the extremes. On one end of the spectrum, we encounter the truly tiny, or at least tiny, on a cosmic scale. The smallest observed black hole, a humble cosmic pebble, might be merely 3.8 times the mass of our Sun. To picture this, imagine the sheer bulk of our Sun, that fiery heart of our solar system, compressed down to an unimaginable density. That is the kind of power held within such a seemingly modest black hole, a testament to the universe's ability to pack immense energy into a minuscule package. It's like holding a single unassuming seed that contains the blueprint for an entire ancient forest. Then, at the other end of this grand scale, we find the true behemoths, the ancient ones that have been silently gathering their power since almost the very dawn of the universe. These are the black holes weighing in at billions of solar masses, cosmic leviathans that dwarf anything we can easily visualize. To call them massive is an understatement. To call them huge barely scratches the surface. Imagine for a moment our entire solar system, with its sun, its planets, its asteroid belts, and its distant icy comets, nestled comfortably within the vast embrace of one of these giants. Their event horizons. The invisible boundaries of no return would easily encompass our entire cosmic neighborhood, leaving us to wonder at the sheer scale of the forces at play. It's like trying to grasp the concept of an endless desert by looking at a single grain of sand. These colossal entities, stretching back to the earliest moments of cosmic time, hint at a universe far older and more complex than our everyday experiences suggest. They are not merely endpoints, but enduring monuments to cosmic processes that have shaped galaxies for eons. Their quiet presence speaks of a continuous cosmic ballet where matter and energy are constantly being reshaped, compressed, and sometimes ultimately silenced. We are merely bystanders observing this grand cosmic drama, learning from the faint echoes and subtle distortions these giants leave in their wake. And with each new observation, each gentle probe into their nature, another layer of the universe's profound mystery is peeled back, revealing depths we are only just beginning to comprehend. The very existence of these black holes, whether small or unimaginably large, points to a ceaseless cycle of creation and transformation, a cosmic breathing in and out that transcends our human timescales. It makes one pause and reflect on the fleeting nature of our own lives, yet also on the enduring power of the fundamental laws that govern such immense phenomena. The quiet immensity of a black hole, drawing everything inward, stands in stark contrast to the explosive birth of stars. Yet both are integral parts of the same cosmic story, a story that continues to unfold silently, patiently, endlessly. It's a lullaby sung in the deepest tones of the universe, a melody composed of gravity and time, of starlight and shadow. These different sizes are not merely arbitrary. They speak to the varied paths through which black holes come into being, each a unique testament to the universe's grand designs. While the ancient supermassive ones might have origins shrouded in the earliest, most chaotic moments of cosmic history, the ones we see being forged today are the dramatic final acts in the life cycles of particularly massive stars. Imagine a star, a luminous fiery orb born into existence as a delicate cosmic balancing act. From its very first breath, it is caught between two immense opposing forces, much like a dancer, perfectly poised between a powerful push and an equally strong pull. The first of these forces is gravity, a ceaseless inward push, relentlessly urging every speck of the star's colossal mass towards its very heart. This inward crush is an immense pressure compressing the star's very essence. But deep within the star's fiery core, something extraordinary is happening, a process that lights up our night sky and powers entire galaxies. Here in the infernal depths, hydrogen atoms, the universe's most abundant building blocks, are squeezed against other hydrogen atoms with such incredible force that they are compelled to combine to fuse, forming a denser, heavier element, helium. It's a cosmic forge, ceaselessly at work transforming the raw materials of creation. This new atomic structure, this freshly minted helium atom, remarkably actually requires less energy to hold itself together than it did when it was two individual separate hydrogen atoms. It's as if a tiny cosmic accountant has balanced the books and found a surplus. The extra energy, this cosmic leftover, finds itself released into the star's core. This released energy, a torrent of heat and light, becomes the second powerful force in our cosmic dancer's balance. It radiates outward from the star's glowing heart, creating an immense outward pressure that directly counteracts the relentless inward pull of gravity. For eons, in this delicate, majestic state, the star will remain relatively stable, a shimmering beacon of light, its fusion furnaces humming steadily until the inevitable moment arrives when its hydrogen fuel, its very lifeblood, begins to dwindle like a flickering candle slowly consuming its wax. This intricate dance between gravity's inward squeeze and fusion's outward push is the story of every star, a testament to the elegant mechanics of the cosmos. Our own sun, a familiar golden sphere in our sky, is in the midst of this very process, a steady, predictable rhythm of creation and transformation. The sheer amount of energy released simply from the slight difference in binding energy is enough to illuminate planets and warm worlds across unimaginable distances. It is a reminder that even the smallest, most fundamental shifts at the atomic level can unleash forces of breathtaking scale, shaping the destinies of stars, and ultimately giving rise to the most enigmatic objects in the universe. The life of a star is a patient, slow unfolding, a testament to the enduring power of these delicate balances. But what happens when the balance begins to tilt? What happens when the cosmic dancer starts to falter in its majestic performance? If the star is truly massive, a cosmic giant among its peers, its story continues beyond the simple exhaustion of hydrogen. Once the primary hydrogen fuel begins to run low, the immense pressure and heat in its core force it to combine the newly formed helium into even denser materials. Imagine, if you will, the star's core becoming an even more sophisticated forge, hammering out heavier elements from lighter ones, carbon, then neon, and eventually oxygen and silicon. Each step in this cosmic alchemy extracts energy, allowing the star to temporarily resist gravity's relentless embrace, maintaining its luminous, fiery form. However, there comes a critical, unavoidable point in this grand stellar narrative. The star begins fusing iron. And this, for a star, is a moment of profound cosmic despair, a turning point from which there is no return. The fundamental issue with iron is that, unlike all the elements that came before it, its formation through fusion does not save any energy. There is no surplus, no extra cosmic warmth to release, no outward push to counter gravity's ever-increasing demand. The iron simply sits in the star's core, a dead weight, growing larger and denser with each new fusion reaction, offering no resistance to the crushing force pushing inward. The delicate balance maintained for millions or billions of years very quickly, catastrophically tips. The energy unleashed in this subsequent collapse is utterly astounding, a spectacle of cosmic violence that beggars belief. But the true force of this apocalyptic implosion is profoundly dependent on the original mass of the star, almost as if the universe is measuring the cosmic hammer before it strikes. Imagine a giant hammer forged in the fires of creation, striking down upon an anvil of unimaginable density. The immense mass of the star, having lost its internal resistance, rushes down to meet its iron core with such terrifying force that the rebound, the cosmic recoil of that cataclysmic blow, is what we call a supernova. It is an explosion of light and energy so vast, so blindingly brilliant, that for a brief moment it can outshine an entire galaxy. From this crackback, this sudden violent exhalation of a dying star, matter and energy are blasted out across the universe in one of the largest explosions possible. This cosmic fireworks display is not merely destructive, it is profoundly creative. Within the unimaginable pressures and temperatures of the supernova, elements, even heavier than iron, are forged all the way up to the heaviest known elements, like uranium. These are the precious building blocks that will one day form new stars, new planets, and perhaps even the very atoms that make up our bodies. The dust of dying stars indeed gives rise to new life. But what remains of the star itself after such a cataclysmic expulsion of its very essence? The answer, like so many things in the universe, depends on the initial conditions, on the precise mass of the star, and thus the raw, unyielding force of that final devastating blow. If the original mass, and consequently the force of the stellar collapse, was too low, if the cosmic hammer was not quite heavy enough, what remains is a neutron star. Imagine a small ball of matter, perhaps no more than 25 kilometers in diameter, a mere speck in the cosmic ocean. And yet this tiny sphere is so densely packed with mass that it holds the equivalent of 1,000,000 Earths. It is a cosmic jewel of unimaginable density, a whisper of a star that refuses to vanish entirely. But if the mass, and therefore the destructive force, was immense enough, if the cosmic hammer struck with an overwhelming power that transcends our wildest imaginings, then something truly profound occurs. At this critical threshold, physics as we know it, the comforting laws that govern our everyday reality, begin to break down, to unravel at the seams. And in their place, we are left with a black hole. It is not merely a dense remnant. It is a fundamental tear in the fabric of space-time, a monument to the universe's most extreme processes, where the very concept of space and time as distinct entities begins to blur, yielding to an entirely new perplexing set of rules, or perhaps no rules at all. This is where our journey truly begins, at the edge of the known, gazing into the vast, silent mystery. When we peer into the cosmos and images reach us of what we are told are black holes, we often see a dark, perfectly spherical silhouette against a swirling backdrop of luminous gas. It's a striking visual, a silent, ravenous eye in the universe. Yet here is a quiet secret. The black sphere you are looking at in these images is not, in fact, the black hole itself. It is merely its shadow, its cosmic imprint on the light around it, the visual manifestation of its unyielding power. Scientists, in their perpetual quest to understand the universe's deepest truths, theorize that a black hole's true form, its very heart, is probably even smaller, far more compact and infinitely denser than a neutron star, which itself is a marvel of compression. Indeed, the prevailing wisdom, a whisper of theory that stretches the limits of our imagination, suggests that the true black hole is likely infinitely small and infinitely dense. We call this theoretical point a singularity. Imagine trying to compress all the mass of a colossal star, or even billions of stars, into a space so tiny it has no measurable size. This is the singularity, a point where our familiar notions of volume and density simply cease to apply, becoming concepts that crumble under the weight of such an extreme reality. From this infinitely small point, forces emanate that so profoundly warp time and space itself that they create the very phenomenon we call a black hole. It's like trying to pinpoint the exact center of a cosmic ripple that spreads out across the entire fabric of existence. However, and this is where the mystery deepens, we don't truly know what the singularity, this theoretical heart of darkness, looks like, or even if it truly exists in the way we imagine. The reason for this profound lack of certainty lies in something called the event horizon, the unyielding boundary that surrounds the black hole. This is the cosmic veil, the point beyond which no information, no light, no signal of any kind can ever reach us. It's like standing outside a perfectly soundproof windowless room, knowing there's something extraordinary happening within, but having no means to confirm it, no way to truly peer inside. What happens within that boundary remains for now a silent, profound secret, guarded by the very laws of physics. We have known since the days of Newton, with his groundbreaking apple, that all objects possessing mass exert gravity, a force that pulls things towards them. It's a familiar, comforting law of the universe. However, a profound shift in our understanding arrived in 1915, when Albert Einstein, with his towering intellect and revolutionary ideas, unveiled his theory of general relativity. This theory didn't just describe gravity as a force. It reimagined it as a curvature, a bending in the very fabric of space-time itself, caused by the presence of mass and energy. It was a beautiful, elegant, and deeply unsettling new way to see the cosmos. And in the wake of Einstein's profound revelation, a contemporary of his, a brilliant and insightful physicist named Carl Schwarzschild, began to reason from these new principles. He pondered the implications of Einstein's equations, specifically What would happen if an object were so incredibly massive, so profoundly dense, that it could create enough gravitational pull to trap even light itself? If light, massless and swift, could not escape, then truly nothing could. Schwarzschild's theoretical calculations birthed the concept of the event horizon, a boundary from which there is no return. So when we look at those captivating pictures of a black hole, that dark silhouette we perceive is not the singularity, the black hole's true infinitely dense heart. Instead, we are witnessing the event horizon, the ultimate demarcation line in space. It is the point where gravity has become so overwhelmingly powerful that light, even in its desperate struggle to escape, simply cannot. It is the cosmic cliff edge where the path bends irrevocably inward. Beyond this threshold, there is nothing but an impenetrable darkness, a silence that swallows all. It is the ultimate expression of cosmic finality, a boundary that marks the end of all possible paths. Outward, a silent, powerful monument to the universe's most extreme embrace. The event horizon's effect on space is one thing, a profound bending of the cosmic pathways. But these cosmic architects of darkness also cast their influence upon another fundamental aspect of the universe, time itself. According to Einstein's profound insights, space and time are not separate entities, two distinct rivers flowing independently. Instead, they are inseparably connected, woven together into a single seamless fabric known as spacetime. Imagine a cosmic tapestry, shimmering and vast, where every thread of space is inextricably linked to a thread of time, creating a unified living canvas. And when a mass, particularly one as immense as the singularity at the heart of a black hole, is introduced, it doesn't just indent this tapestry. It stretches and distorts space-time with an unimaginable intensity. With the singularity's infinite point of mass, the warping becomes so extreme, so utterly profound, that the event horizon also marks another startling boundary, the point where time itself, as we understand it, essentially stops. Within the event horizon, the very concepts of where and when lose their familiar meaning. It's a place where there is no longer a clear direction, no true sense of progression or location. The cosmic coordinates that define our reality simply cease to function in any way we can comprehend. It's like stepping into a dream where the rules of logic gently dissolve, leaving only an ethereal, timeless present. This deep connection between space and time and its extreme distortion near a black hole produces a truly fascinating phenomenon, a cosmic trick of perception, especially for an outside observer. Watching matter fall into one of these silent abysses, from their perspective, from a safe distance far away, as a piece of matter or an intrepid astronaut approaches the black hole, it will appear to slow down. Imagine watching a distant ship, slowly losing speed as it approaches a mysterious fog bank, its journey seeming to stretch out into an eternity. This slowing will continue until just before it reaches the event horizon. The object will seem to stop altogether, frozen in a timeless tableau against the dark backdrop. You, the distant observer, will never actually witness the matter truly cross the event horizon. There will be no satisfying absorption, no dramatic final plunge into the cosmic maw. Instead, the matter will gradually dim, its light stretching and reddening its movements, becoming ever more sluggish, until finally it fades entirely from your sight, becoming an invisible ghost in the cosmic ballet. It's a gentle vanishing, a subtle erasure from the observable universe, leaving behind only the question of its fate within the timeless depths. This is not merely a visual illusion. It is a profound consequence of how black holes warp time itself, making the moment of crossing an infinite, unreachable event for anyone observing from the outside. For a long time, when the concept of black holes was first theorized, these celestial anomalies remained purely in the realm of imagination, mathematical curiosities on paper. Astronomers and physicists, despite the elegance of the equations, were deeply uncertain if black holes were actually real, if such fantastical objects could truly exist in the tangible universe. They were whispers in the dark, elegant possibilities but yet to be confirmed. It was only some 4 decades later, in a quiet breakthrough that echoed across the scientific community, that the first tentative evidence of a black hole was finally recorded, ushering these theoretical constructs into the realm of observable reality. The year was 1964, a time when humanity was just beginning to explore the cosmos with newly developed X-ray satellites, tiny ears, listening for the high-energy whispers of the universe. Scientists sifting through the data noticed a peculiar object in the constellation, Cygnus. This unseen entity seemed to be emitting an unusually large amount of X-rays, a powerful invisible beacon in the night sky. What surprised them, what truly piqued their scientific curiosity, was that while this object was a strong X-ray source, they could not see the object itself in visible light. If it were a typical star, even a very hot one, it ought to emit a harmonious symphony of light, both X-ray and visible radiation. But here was a silent, invisible producer of powerful X-rays, a cosmic anomaly. Scientists, with a blend of mystery and scientific precision, named this enigmatic source Cygnus X1. Then, in 1970, as telescope technology continued its quiet advancement, offering ever sharper eyes to peer into the cosmic depths, a crucial piece of the puzzle slowly revealed itself. Scientists observed that whatever Cygnus X1 was, it had formed a binary orbit with a visible supergiant star in its system. This cosmic dance partner was the key. By meticulously observing the visible star's orbital period and its subtle wobble, scientists were able to calculate the mass of its invisible companion, the elusive Cygnus X1. The revelation was startling. This unseen object was a staggering 15 times more massive than our own Sun. This was a pivotal moment. The densest known object at the time, a neutron star, had an upper limit, a cosmic ceiling of about 3 times the mass of the Sun. Any object more massive than that, it was theorized, could not remain a stable neutron star. Its own gravity would overwhelm its internal resistance. So, with Cygnus X1 weighing in at a colossal 15 solar masses, scientists realized that this invisible X-ray emitting powerhouse was most likely the first ever discovered black hole. It was a confirmation of a theoretical whisper, a tangible proof that these mind-bending objects truly existed, not just in the elegant equations of physics, but out there silently warping the very fabric of our universe. Since that pivotal discovery, our cosmic vision has sharpened, and we have uncovered many more black holes, each adding a new layer to our understanding of these mysterious entities. Among these numerous discoveries, a particularly grand scale of black holes has emerged, often found lurking like ancient sentinels at the very centers of galaxies. These are the supermassive black holes, cosmic anchors, around which billions of stars gently swirl. We've even managed, with incredible technological leaps and patient observation, to take what might be described as photos of some of them. Not direct images of the black hole itself, but dark blots, profound shadows against the swirling incandescent rings of matter that tirelessly surround them and slowly, inexorably fall into their grasp. This luminous cosmic halo is known as the accretion disk, a vibrant, fiery whirlpool that reveals the black hole's otherwise invisible presence. It is through these very accretion disks that black holes, otherwise silent and dark, can still be detected across vast cosmic distances, primarily through their powerful X-ray emissions. While black holes, by their very nature, cannot emit visible electromagnetic radiation themselves, for nothing, not even light, can escape their gravitational prison. The X-rays that come from them actually originate from these swirling, fiery accretion disks. Here, in falling matter caught in the black hole's inescapable gravitational embrace is subjected to unimaginable forces. The intense friction generated as particles rub against each other at near-light speeds heats this matter to millions of degrees Celsius, turning it into a superheated plasma that screams with X-ray light. It's a paradoxical situation. The black hole itself is the epitome of darkness, yet its presence can ignite the brightest, most energetic phenomena in the universe. A cosmic lighthouse powered by its insatiable hunger. However, if a black hole has no infalling matter, if its cosmic larder is empty, and its gravitational pull has not recently ensnared an unlucky star or gas cloud, it remains essentially invisible. Without a brightly glowing accretion disk to spot it, becomes a silent phantom, a dark blot against the backdrop of the stars, nearly impossible for our most sophisticated instruments to detect. It drifts through the cosmic ocean, a true ghost in the machine, known only by the absence of light. Exploring black holes remains a continuously developing field in physics, a frontier of human inquiry where each answer often sparks a dozen new questions. There is still so much to learn, so many layers of cosmic mystery yet to be gently peeled back. From what we have managed to glean so far, a natural question arises, one that touches upon the very concepts of permanence and ultimate fate. Could a black hole ever truly stop being a black hole? Or are they destined to grow forever, silently absorbing matter and radiation, until in the unimaginable reaches of the cosmic future, there is no light, no energy, no substance left in the entire universe? On the surface, it would certainly seem so, an ultimate inexorable force of cosmic consumption. However, in 1974, a quiet revolution in our understanding of black holes was proposed by the brilliant physicist Stephen Hawking. In his seminal paper soberly entitled Black Hole Explosions, he postulated that there was surprisingly actually a way that energy, and therefore mass, could indeed leave a black hole. It was a radical idea, seemingly defying the very definition of a black hole, a whisper of escape from the ultimate cosmic prison. But to truly grasp the profound implications of Hawking's revelation, we must for a brief moment venture into some extremely weird theory, a realm where our everyday intuition simply cannot follow, and where the universe reveals its strangest, most counterintuitive truths. We need to gently, carefully examine some fundamental principles of quantum mechanics, the strange rules that govern the universe at its most minute scales. But first, let me pose a difficult, almost Zen-like question, a puzzle for the sleepy mind. What truly is nothing? Imagine for a second, if you will, a perfect patch of space utterly devoid of anything. It has no atoms of space dust, no stray photons of light, not even the faintest whisper of radiation passing through it. As near as can be observed, absolutely nothing exists within it. It is a vacuum beyond vacuums, a void of ultimate emptiness. And yet, is there truly absolutely nothing there? Or does something fundamental, something profoundly subtle, exist even in this perfect, pristine emptiness? We can tell that this is indeed the case, that this nothing is not truly empty when a beam of light travels through it. If you are familiar with the properties of light, you will know that light in its essence is not merely a stream of particles. It is also waves, waves of electrical and magnetic charge, constantly propagating with each other, dancing forwards in a straight line through the cosmic expanse. But here's the quiet puzzle, the gentle thought provoker. A wave implies something is waving. A wave in the sea is the propagation of energy moving through the water. The water itself isn't traveling to the shore, but the energy is. Similarly, a sound wave moves by passing energy between air particles, with each particle only moving a tiny bit, becoming energized, and then gently passing that energy to the next particle in line. But in our perfect vacuum of space, where there is truly nothing, where our photon of light is gracefully traveling in waves, have you ever stopped to wonder what exactly is waving? What is the medium, the hidden fabric through which light ripples and dances? This subtle question hints at a fundamental something that exists even in nothing, an unseen tapestry, a foundational fabric that makes up all of reality itself, stretching silently throughout the universe. Quantum physicists, those explorers of the incredibly small, call this mysterious something a quantum field. These quantum fields are notoriously tough to wrap our minds around, like trying to hold smoke in your hands, but they are inescapably important when it comes to understanding the ultimate fate, and indeed, the quiet evaporation of a black hole. So how do these abstract quantum fields and the notion of exploding black holes tie together in this grand, strange tapestry of cosmic understanding? Returning to Hawking's groundbreaking paper, A Quiet Whisper That Changed the Landscape of Physics, he hypothesized that black holes would slowly, almost imperceptibly, release energy over vast expanses of time. Initially, these would be tiny, almost immeasurable quantities, like faint echoes in a silent hall. But crucially, because energy and mass are simply two expressions of the same fundamental thing, as elegantly captured by Einstein's famous equation E=mc², this subtle release of energy inevitably resulted in a proportional reduction in the black hole's mass. It was a cosmic diet, slow and steady. However, and here's the surprising twist in this quiet cosmic drama, as the black hole shrinks, as it slowly sheds its mass into the vacuum of space, the rate of energy release would paradoxically begin to speed up. It would get faster and faster, an accelerating evaporation, until in the very last fleeting moments of the black hole's unimaginably long life, it would release a burst of energy that was truly gargantuan in its scale, a final brilliant flash before vanishing entirely, leaving behind only the echo of its existence. It's like a colossal iceberg slowly melting, but then in its final moments, exploding in a blinding mist. But how could this possibly be true? It is a well-known foundational principle that an event horizon is inescapable, a one-way door from which no energy, no particle, no information can ever leave. So how then could radiation ever escape it and eventually cause such a dramatic black hole explosion? The answer is a strange one, a deep dive into the unintuitive ideas of quantum theory concepts that completely go against our day-to-day experience of the world, much like trying to walk on water. But if it's true, and the evidence is slowly, gently building, then I hope you're prepared for the universe to be a whole lot stranger, a whole lot more wondrous than you first thought. It's a journey into the heart of paradox, where what seems impossible becomes subtly, beautifully real. To begin understanding Hawking's theory, to truly step into this ethereal landscape of quantum weirdness, we first need to embrace the subtle, profound idea of quantum fields. Remember that earlier question, the one that lingered in the quiet emptiness of space? What exactly is waving when light travels through a vacuum? The very fact that light ripples and dances through even a completely empty patch of space reveals a profound truth. There must be something existing, something fundamental even in that apparent nothingness. Otherwise, light simply wouldn't be able to wave, wouldn't be able to propagate its electrical and magnetic embrace across the vast cosmic distances. Scientists with a gentle sense of wonder and precise mathematical rigor call this fundamental fabric of reality a quantum field. In fact, the universe in its intricate design is believed to be woven not just from one, but from several quantum fields, all overlapping each other like layers of invisible shimmering silk. These fields are not confined to specific pockets of space. No, they cover every single patch of the universe, whether it be in the past, the present, or the unfolding future. Each individual quantum field quietly defines a particular type of something. For instance, one field might silently define all of the electrons in existence, giving them their very being and properties. Another field might define the quarks, those tiny ephemeral particles that make up the very heart of an atom. They are the unseen blueprints, the fundamental hums of creation. In regions where to our macroscopic eyes, nothing can be found, where space appears utterly empty, the quantum field is relatively quiet. Imagine it like a guitar string that hasn't been strummed lying perfectly still waiting. Or think of it like a graph that has a zero value, a flat, serene line of calm. But wherever at any point in time and space, mass or energy can be found, the quantum field at that specific point is resonating, humming with activity. When this resonance, this subtle vibration reaches a certain threshold or quantity, the universe in its elegant display expresses that resonance to us as a tangible something, perhaps an electron or a photon, a tiny packet of light. It's as if the string has been plucked and its vibration reveals the note. It's profoundly important to grasp that in this deep and subtle theory, the resonance of the field is not merely reacting to a piece of matter. No, it is the matter. An electron, that tiny fundamental particle, is nothing more than a resonating section of the quantum field that defines electrons. The field isn't holding the electron, it's being the electron. This astonishing truth holds for all energy and all matter too. Think of a melody being played. The notes aren't separate from the song. They are the song. According to Einstein, as we softly reminded ourselves earlier, energy and matter are but two sides of the same coin, two different expressions of an underlying reality. In this profound quantum view, the entire universe you see around you, from the distant stars to the book in your hand, is nothing more than resonating quantum fields. In this ethereal, beautiful way, the theory portrays all of the universe as an incredibly complex ongoing song being played on these unseen fundamental fields. It's a truly beautiful image, if nothing else, a symphony of vibrations, creating the tangible reality we perceive. Every atom, every ray of light, every thought is but a fleeting note in this grand cosmic composition. But why does this profound understanding of the universe matter so deeply? Why is it so important, so crucial to define reality in this way as a symphony of vibrating fields? Well, the answer leads us to another corner of quantum physics, an idea that defies our everyday common sense, but is fundamental to the universe at its smallest scales. Heisenberg's uncertainty principle. This principle, a gentle whisper of cosmic mystery, reveals that sometimes even in the deepest silence, the strings of the universe simply begin strumming themselves, creating a faint, restless hum. Without delving too deeply into the intricate mathematical dance of this aspect of quantum physics, it essentially tells us that when we are looking at really tiny objects, things on the atomic or subatomic scale, it becomes fundamentally impossible to know too much about them simultaneously. For instance, you cannot precisely know both the location and the direction of travel of an electron at the exact same moment. It's a cosmic riddle that plays out in the smallest arenas. As soon as you try to pinpoint the electron's location, perhaps by shining a tiny light on it, it inevitably bounces off whatever you are using to measure it. And in that very act of measurement, its direction of travel is disturbed, leaving you no longer certain of where it's headed. Conversely, if you know its direction with certainty, then, according to this principle, you cannot pinpoint its precise location. It's a cosmic dance where the act of observation changes the observed, not because our methods are clumsy, but because it's a fundamental law embedded in the very nature of the universe itself. This Heisenberg's uncertainty principle is not just about the limitations of our measuring devices, the inadequacy of our cosmic eyes. No, it delves deeper than that. It is a profound statement about the inherent nature of reality at the subatomic level, a quiet acknowledgement that we cannot fully grasp every detail about these minuscule particles simultaneously. But when you gently apply this principle to our concept of quantum fields, the picture becomes even stranger, even more wondrously counterintuitive. Imagine those quiet flat strings of the quantum field lying still in the empty vacuum. According to Heisenberg's uncertainty principle, these quantum fields are not truly still. They fluctuate everywhere, even in the deepest void. And because of these fundamental fluctuations, something truly astonishing can happen. Particle and antiparticle pairs can actually pop in and out of existence. They are like tiny shimmering bubbles that momentarily appear from nothingness only to vanish just as quickly. The how and why of this phenomenon get incredibly complicated, a deep dive into the very bedrock of quantum electrodynamics. But the fundamental idea is that the universe quietly allows this spontaneous creation as long as these virtual particles exist for only a very, very short period of time, precisely ruled by the strictures of uncertainty relations. It's a cosmic loophole, a fleeting permission slip granted by the laws of quantum mechanics. You might pause here, a gentle frown of wonder, perhaps touching your brow thinking, this can't possibly be a real thing. Matter does not just spontaneously pop into existence from nowhere. Surely we would have noticed this by now in our everyday lives. And you would be right to question. However, in a profound and meticulous experiment conducted by the Dutch physicist Hendrik Casimir, evidence was found that quietly suggested this strange phenomenon might indeed be happening. Casimir, with a brilliant spark of insight, took 2 plates of conductive metal, perfectly flat and polished, and placed them incredibly close together, almost touching, but not quite. The distance was so minute, so infinitesimally small, that only certain sizes of smaller virtual particles could spontaneously pop into existence in the tiny gap between them, like only certain wavelengths of light can pass through a narrow slit. This minuscule gap effectively limited the number of such virtual particles that could pop into existence between the plates. However, on the outside of the plates, the vast open universe awaited, allowing all types and sizes of virtual particles to flicker in and out of existence freely. This subtle difference meant that there was a slightly greater pressure exerted by the multitude of virtual particles on the outside of the plates compared to the constrained number inside. Theoretically, this larger pressure from the ceaseless activity of virtual particles on the exterior surfaces should subtly push the 2 plates together ever so slightly. And in the meticulous test performed by Casimir, this proved to be precisely the case, offering a quiet, undeniable whisper of evidence for the restless hidden life within the vacuum. It was a groundbreaking moment, a confirmation that even nothing is teeming with unseen activity. You might still be wrestling with the concept, feeling a gentle pushback from your common sense, thinking that particles appearing out of nowhere seems to defy the fundamental laws of conservation of matter and energy, those bedrock principles that assert nothing can be created or destroyed. And you would be absolutely right to feel that way. So to elegantly balance the cosmic scales, whenever a virtual particle spontaneously appears, a second particle also pops into existence at the exact same moment, destined to pair up with the first particle. But here's the crucial, elegant twist. While one of these particles is ordinary matter, the other is its mirror image, its cosmic twin, antimatter. Imagine it like a cosmic accounting trick. One particle is a +1 on our universal balance sheet, while its antimatter twin is a -1. Together, they keep things perfectly balanced, always maintaining the overall sum at a precise 0. The universe, in its profound wisdom, is perfectly happy, its fundamental laws upheld even in these ephemeral creations. And on top of that, these fleeting fluctuations in the quantum field quickly, almost instantly, crash into each other. When a particle meets its antimatter counterpart, they undergo a process called annihilation, releasing a burst of pure energy and effectively removing both from existence once again. It's a brief, brilliant flash, a fleeting cosmic dance before they vanish into the quantum foam. This rapid annihilation is precisely why we don't normally have to worry about these virtual particles appearing and disappearing in our everyday lives. They are too fleeting, too quick to resolve their existence to ever have a noticeable impact on our macroscopic world. They are the unseen hum, the subtle breath of the universe, always there, but rarely perceived directly. As a gentle side note, a fascinating theory, a whisper of cosmic speculation, suggests that antimatter might simply be matter that is moving in the opposite direction through time. It's a concept that stretches the mind even further, adding another layer of bewildering beauty to our understanding of the universe. But that perhaps is a level of quantum weirdness that we don't need to delve into here, saving it for another quiet, contemplative session. The important part for our current journey, for understanding the profound secret of black holes, is this: the quantum fields that weave the fabric of reality are constantly resonating, constantly fluctuating, and for the most part, constantly canceling each other out. This ceaseless dance of creation and annihilation is precisely why, for the vast majority of the time, empty space appears to our senses to be truly empty. It is a quiet, ceaseless ballet of emergence and disappearance, upholding the cosmic balance. However, what would happen? What profound change would occur if you were able to stop only some of those quantum fields from resonating, leaving others to fluctuate freely? And this, dear listener, is where our majestic black holes quietly step onto the stage, becoming the key to unlocking this very mystery. Black holes, with their immense gravity and their enigmatic event horizons, act a bit like putting your thumb gently yet firmly on the guitar string of the universe. Due to the extreme curvature of spacetime near their boundary, certain resonances, certain specific vibrations in the quantum fields are subtly dampened, down-muted almost, while others are allowed to continue their free, vibrant hum. It's a selective silencing, a profound distortion of the quantum symphony. Hawking, in his brilliant leap of intuition, imagined sketching a line through time in a patch of space where a black hole was born, a conceptual timeline that stretched from moments before the black hole's dramatic emergence into the deep future, long after its formation. He envisioned a quantum field resonating along this cosmic timeline, a continuous hum of existence. Before the birth of the black hole, all was normal, a perfect quantum equilibrium. All the quantum fields were resonating freely, their spontaneous particle-antiparticle pairs appearing and annihilating, perfectly canceling each other out, ensuring the vacuum remained, on average, perfectly empty. The cosmic books were balanced, the symphony was in harmony. However, the dramatic emergence of the black hole's event horizon profoundly changed the curvature of space around it, and it was outside this event horizon, in the distorted but still observable universe, that Hawking realized something truly astonishing. Certain quantum pulses, certain spontaneous virtual particles, were now tragically missing their opposite numbers, their cosmic twins. The extreme curvature of spacetime, subtly influenced by the event horizon, had pulled one half of a spontaneously created particle-antiparticle pair across the boundary, forever separating it from its twin. As he meticulously looked at the math, a profound truth unveiled itself. Not everything was being canceled out anymore after the black hole had formed. The symphony was subtly out of balance, indeed outside the event horizon. Gently traveling away from the black hole, he found resonances that perfectly matched the shape of thermal radiation, flying away into space. This was a profound, almost unbelievable discovery. Radiation is energy, and energy, according to the fundamental laws of conservation, cannot simply form from nothing. Since the black hole, in its silent, powerful presence, was effectively creating and emitting this radiation, the black hole itself would, by necessity, have to pay the cosmic price. Every single piece of this newly discovered Hawking radiation would thus coincide with an equal corresponding amount of energy lost from the black hole's own immense mass. In time, over unimaginable eons, this slow, silent bleeding of energy would gradually reduce the black hole down to nothing, a profound, gentle evaporation. It was a revelation that defied all prior expectations, turning the ultimate cosmic devourer into a slow, patient giver, if it truly exists. Hawking radiation is a phenomenon of profound subtlety, almost like money spontaneously appearing outside of a bank, while simultaneously and mysteriously an equal amount of money quietly vanishes from the vault inside the bank. It's a cosmic ledger that always balances even in the most bewildering circumstances. However, this remarkable theoretical prediction is also extremely difficult to prove, a whisper so faint that our current instruments struggle to hear it amidst the cosmic chorus. Hawking himself predicted that this radiation would be infinitesimally cold, far colder than the pervasive background cosmic radiation that fills the universe, a relic of the Big Bang itself. Moreover, the wavelength of this predicted radiation would be astonishingly long as the black hole's event horizon itself. And given that some black holes possess event horizons the size of entire solar systems stretching for billions of kilometers, we simply have no way with our present technology of detecting this kind of radiation directly. It's like trying to hear a single drop of rain fall in the middle of a roaring ocean. We would perhaps only truly see it once the universe itself had grown old and cold, once all the other brighter, louder cosmic phenomena had faded away, leaving nothing else to get in the way of its faint signal, which by that distant, desolate time would probably mean we weren't around anymore to do the detecting anyway. A melancholic thought for our brief human existence. However, in spite of the profound observational objections to its direct detection, the intricate mathematics behind Hawking radiation seems to be remarkably sound, robust in its elegant complexity. And quietly, persistently, scientists have recently taken significant steps toward proving its underlying principles in the quiet, controlled confines of the lab. This is a testament to the human spirit of inquiry, constantly pushing the boundaries of what is known. At the Technion Israel Institute of Technology, researchers, driven by a deep curiosity about Hawking radiation, came up with an ingenious idea to circumvent the immense difficulty of measuring a real-life black hole directly. They did this by creating something truly remarkable, an analog black hole, a sort of cosmic mimicry right here on Earth. Specifically, they fashioned a sonic black hole, a clever system designed to mimic the properties of a gravitational black hole, but using sound waves instead of light and spacetime. Their cleverness lay in relying on the fundamental fact that sound moves much, much slower than light. This disparity in speed makes it far easier to create a medium that moves faster than sound within a laboratory setting. Imagine a river flowing so swiftly that any sound waves trying to travel upstream against the current of the river itself could never quite escape it. They would be pulled back by the overwhelming flow. This sonic river, moving faster than the sound it contains, acts precisely like a black hole for sound waves. Any sound waves traveling in the same direction as this supersonic medium simply cannot escape it, just as light cannot escape a gravitational black hole. Interestingly and profoundly, Hawking's original mathematical equations, initially formulated for gravitational black holes, worked for these sonic black holes just as well. The universal elegance of the physics held true across different domains. And so, if the math was correct, Hawking radiation ought to be detected emanating from this sonic analog. After repeating the experiment an astonishing 97,000 times over 124 days of continuous patient experimentation, the dedicated researchers detected multiple clear instances of Hawking radiation. And even more remarkably, they observed that its behavior perfectly matched Hawking's theoretical predictions for how his radiation might behave. It was a triumph of ingenuity and perseverance. While this groundbreaking laboratory experiment does not definitively prove that Hawking radiation is real for actual cosmic black holes, the leap from sound waves to light and gravity is still a significant one. The fact that Hawking's elegant mathematics worked so beautifully for this sonic analog is a powerful, compelling implication that he might indeed be on to something profoundly true. It's a strong whisper from the universe, suggesting that Hawking radiation might just be real, a quiet, persistent hum emerging from the very edges of existence, waiting for us to finally hear it. So if you were to, by some fantastical cosmic mishap, fall into a black hole, could you ever escape? The simple, quiet answer for all practical purposes is probably not. Once past that event horizon, the arrow of time points only inward, and all paths lead to the singularity. However, if you were to wait until almost the very end of the universe, an unimaginably vast expanse of time when the black hole had radiated almost all of its immense mass away through the subtle process of Hawking radiation, then perhaps the mass and energy that once made up your existence might be completely removed from inside the event horizon. Does that count as escaping a gentle philosophical question for the ages? It's probably not a very appealing prospect for you or for any of us. The notion of waiting for trillions upon trillions of years for your constituent particles to re-emerge scattered across the vast cold vacuum is hardly a comforting thought of freedom. Probably it's still best just not to go in at all. The allure of the unknown is strong, but some cosmic destinations are best observed from a very, very safe contemplative distance. And that's not the only weird thing about black holes. Their very existence and the subtle implications of Hawking radiation hint at something quite worrying, something profoundly unsettling about our own perceived reality. Imagine walking on a soft, sandy beach. As your foot presses down, it leaves a distinct imprint, a clear footprint in the sand. There is no question in your mind that it is your foot that caused the footprint. The order of causality is beautifully clear here. It seems almost laughable to even need to assert such a simple truth. You made the footprint did not make you. But what if just for a quiet, unsettling moment it did? What if I were to gently whisper to you that on the cosmological scale, the fundamental intuitive relationship between foot and footprint, between cause and effect, might be a little more blurred, a little less certain than you would intuitively think. And shockingly, due to the peculiar nature of black holes and the subtle, persistent presence of Hawking radiation, there is some evidence, some faint cosmic hint that this might just be the case. It's a thought that gently shakes the very foundations of our common sense, urging us to reconsider what we truly know about cause and consequence. To begin unraveling this perplexing idea, we're going to need to look at a principle that predates even Einstein, a concept called relativity, but not the one you might immediately think of. We'll start with Galilean relativity, first described with elegant simplicity by Galileo Galilei in 1632. The core idea of this form of relativity is a profound and deceptively simple one. There is no fundamental difference from an internal perspective between being completely still and moving at a perfectly continuous, unwavering speed. It's a quiet challenge to our everyday experience of motion. Imagine two identical rooms, perfectly enclosed and windowless. One room is situated firmly on land unmoving. The other is aboard a ship silently gliding across a perfectly calm sea, with no rocking or jolting whatsoever. Both rooms are soundproof, isolating you from any external clues. The only real difference between the two rooms is that one is moving at a steady speed and the other is not. Can you, from inside either room, truly tell the difference between the two? You might instinctively think that you would be able to sense the movement, feel the ship gliding. But surprisingly, this is not the case for uniform motion. Consider your current state. Right now, as you sit or lie peacefully, you are in fact silently careening through space at an astonishing speed of 110,000 kilometers per hour, simply due to the Earth's majestic movement around the sun. Yet, if you're sitting at home, perhaps sipping a warm drink, it's highly likely you would confidently say you weren't moving at all. In truth, Galileo, with his brilliant insights, realized that there was no physical test that could be done from inside these perfectly isolated rooms to tell the difference between the two scenarios. He even found that if you gently dropped a ball within the ship from your perspective inside, it would appear to fall straight down, just as it would on land. Even if, from the perspective of a person standing on the shore watching the ship pass, the ball would appear to be falling diagonally due to the ship's forward motion. Galileo's profound realization was that if you remove all external frames of reference, imagine being truly alone in the vast empty expanse of space. There is absolutely no way of telling if a distant planet is moving towards you or if you are moving towards the distant planet. According to this principle of relativity, both interpretations are equally valid, equally true. It's a gentle dissolution of absolute motion. You might have quietly noticed this yourself if you've ever looked out of the window of a train, just as another train suddenly passed by, quickly overtaking you. Although both trains are going forwards, and the other train is simply going faster than yours, because you no longer have a fixed frame of reference to compare your motion to, it might momentarily look as if your train is suddenly going backwards. It's a subtle trick of perception, revealing the fluid nature of relative motion. Einstein, with his even deeper insights, took this fundamental idea further with his equivalence principle. Here, he revisited the concept of two isolated rooms, but this time, he was making a profound observation about gravity itself. Imagine you are inside a windowless room, floating silently in the perfect vacuum of space, experiencing true weightlessness. Now imagine that someone unseen suddenly starts accelerating your room in the up direction, perhaps by strapping a powerful rocket to its bottom. If that rocket accelerated at precisely the right speed, the exact rate of Earth's gravity, then the feeling inside your room would be utterly identical to if you were simply standing in a stationary room on the surface of Earth. In other words, there is fundamentally no way to truly tell the difference between the acceleration caused by the familiar pull of gravity and the acceleration caused by a constant push from a rocket. Of course, this assumes you couldn't feel the rocket shaking you with all its rumbling and vibrations. Those are merely practical details. Both sensations, the pull of gravity and the push of acceleration, are at a fundamental level the same thing. It's a profound thought, suggesting that what we perceive as gravity might be a form of acceleration, a constant, subtle push in disguise. Both of these principles, Galilean relativity and Einstein's equivalence principle, rely deeply on the concept of inertia. Inertia is that quiet fundamental stubbornness of objects. They do not like to move if simply left on their own, and once they have started moving, they do not like to stop. To make a mass do something different from what it is already doing, to start it moving, to stop it, or to change its direction, a new external force must be applied. Otherwise, it will remain inert, stubbornly continuing its current state of motion. It's a fundamental resistance to change, a deep-seated preference for remaining as it is. But why would it feel to the man in the room with the accelerating rocket as if he were under the familiar effects of gravity? Or perhaps a more intriguing, more profound question: why would it feel to us here on Earth as if we were being constantly accelerated upwards by the effects of some unseen rocket? Surely the Earth is not expanding in all directions at once, ceaselessly pushing us with it. While this is true, a direct upward push is not what's happening. Einstein, in his brilliant leap of understanding, realized that the two sensations felt similar because at a deeper level, they both represented the same fundamental thing, a form of acceleration. However, there is another more elegant form of acceleration that better explains how gravity truly works, one that is far more nuanced than simply applying a direct force to an object pushing it like a rocket does. Consider for a moment a spinning fairground ride, the kind that looks like the barrel of a drum. You stand with your back leaning against the inside of its walls. If you have ever been on such a ride, you will know the astonishing power of changing direction as a profound form of acceleration. As the ride gets up to speed, spinning faster and faster, you feel a constant unyielding force pressing you firmly against the wall, even when the ride spins at a perfectly constant speed. This is because your mass with its inherent inertia is constantly trying to move in a straight line at each point in the ride. But the relentless curvature of the ride's wall is forcing you to alter your direction, to deviate from your preferred straight path. The battle between your inertia, which tries desperately not to change what you are doing, and the wall, which is constantly trying to alter your direction of travel, manifests as the powerful force you feel pressing you outward. And as far as acceleration is concerned, there's not much fundamental difference between the Earth beneath you accelerating you up by resisting your tendency to fall straight through it, and you trying to accelerate down by being forced into a curved path. It's a subtle but profound insight into the nature of apparent forces. Einstein, with his profound and almost mystical understanding of the universe, realized that this form of acceleration, the constant struggle against a curving path, was the most elegant and accurate explanation for gravity itself. He did not see gravity as a force pulling objects together, but rather as a profound distortion of the very arena in which those objects moved. He came up with a revolutionary theory, a breathtaking cosmic vision that matter and energy do not simply exist in space, but rather cause a warping, a subtle bending in the space around it. Imagine, if you will, a heavy ball placed upon a stretched rubber sheet. The ball doesn't pull the sheet, it simply depresses it, creating a curve. Any smaller object rolling nearby would then be drawn towards the heavier ball. Not because the ball is actively pulling it, but because the very surface it rolls on has been gently yet profoundly curved. The larger the mass, the greater the curvature, the deeper the cosmic well. And once space itself was curved, any object attempting to travel through it would find its path subtly yet inevitably deflected by that curve. In the poetic and deeply insightful words of physicist John Wheeler, a titan of cosmic thought, space tells matter how to move, matter tells space how to curve. It is a beautiful reciprocal dance, an elegant cosmic conversation that defines the very structure of our universe. For small masses, like a tiny pebble on our cosmic rubber sheet, this curve in space would be very slight, almost imperceptible. But in the presence of incredibly dense masses, like the collapsed heart of a dying star, this curvature could become so immense, so overwhelmingly profound, that it would be utterly impossible for an object that got too close to it to ever escape. These are precisely the extreme conditions we find near a black hole at the boundary of its event horizon, where the fabric of reality folds in on itself. So, gently returning to our very first analogy, that quiet thought provoker of the footprint, and the foot if a black hole is the foot, then the profound curvature of space that surrounds it is the undeniable footprint. It's a fascinating and almost tangible way to see all of this in action, to understand the intuitive leaps and rigorous logic that led Einstein to conclusions which even 100 years on have been almost universally validated by generations of dedicated scientists. There is so far nothing particularly weird about any of this. Understanding the exact mechanisms behind this cosmic dance, the elegant interplay of matter and curved space, doesn't inherently make it any stranger. The black hole, in its silent majesty, tells space how to curve, and once curved, any object moving near it is simply told how to move, following the path of least resistance through the distorted landscape. Nothing here is truly outside our expectations, based on careful day-to-day observations of the world around us. But then, as we gently shift our gaze and begin to look closer to delve into the subtle, perplexing nature of Hawking radiation, something truly very strange, very unsettling, begins to happen. The most important thing to bear in mind about this elusive radiation for the purposes of our current contemplative discussion is that it is non-local. This means quite profoundly that it does not appear directly from the black hole itself, not from the singularity at its heart. Instead, it appears seemingly from the very area of space around the black hole. This is a crucial distinction that unravels our intuitive understanding of cause and effect. To be clear, when we say around it, we do not mean beyond the singularity of the black hole within that infinitely dense point, which in any case is already hard to define. In that region, space as we know it simply ceases to exist, dissolving into a realm beyond our current physics. Remember, the dark, mysterious ball you see in images is simply the demarcation point, the event horizon, the boundary between inescapable curvature and escapable curvature. It is not the physical black hole itself. Nor do we even mean right up against the event horizon, though that is sometimes how this complex theory is simplified in popular portrayals. People sometimes speak of two particles spontaneously popping into existence right at the edge of the event horizon, with the antimatter particle just inside it destined to fall in, while the normal particle is just outside and so escapes into the cosmos. However, that simplistic image, while helpful for initial understanding, is not precisely what is happening in the full subtle theory. Instead, the region of space where this Hawking radiation can spontaneously pop into existence is vast, stretching outwards for several times the size of the event horizon itself. This distance can be truly immense, up to billions of kilometers away from the black hole's core. And when we consider that the largest black holes we have encountered can comfortably fit multiple solar systems side by side inside of their event horizon, the idea that a photon of radiation can spontaneously pop into existence at such a colossal distance, billions of kilometers outside the event horizon, is truly wonderfully crazy. It happens, Hawking suggested, even in a place where there is literally, to our macroscopic senses, nothing there. It is a whisper born of the vacuum itself, a ghost in the machine of spacetime. So in short, it is not so much that Hawking radiation is coming from the black hole directly, like steam rising from a kettle. Instead, it is coming into existence from the curvature of space that the black hole is creating, the profound distortion of the cosmic fabric, and crucially, this can happen quite far away from the black hole itself in a region of space that still seems to our eyes like empty vacuum. But if that is truly the case, then things begin to work in a way that is completely opposite to what we might intuitively expect. It turns our comfortable notions of cause and effect gently upside down, inviting us to ponder a deeper, more paradoxical reality. Consider for a moment what happens in this profound, counterintuitive order as energy in the form of Hawking radiation quietly leaves the curvature of space around the black hole. The curvature itself lessens. This happens because of something known as the fundamental conservation of energy, a bedrock law of the universe that demands balance. And as this subtle reduction of curvature occurs as the space around the black hole gently flattens out the black hole itself, then shrinks. This is truly wonderfully crazy. This is like our earlier analogy of the foot and the footprint, but in reverse, it's like the footprint on the sand spontaneously getting smaller, and in response, the foot that made it also shrinks accordingly. It feels profoundly wrong, a violation of our deep-seated understanding of how the world works. Surely things can't possibly work that way, can they? And yet Einstein, in his profound genius, hinted that such a thing might indeed be possible, nestled within one of his most famous equations. He stated that the curvature of space-time was proportional to the mass energy of an object. But here is the subtle distinction. The quiet ambiguity. Proportional is not the same as causational. There is no inherent presupposition in that relationship that one causes the other, only that they exist in a balanced, linked relationship. We are perfectly comfortable with the idea of changing the mass of an object, and as a direct result, changing the curvature of spacetime around it. That fits our intuition perfectly. But Einstein's equation works just as well if you go the other way around. If you change the curvature, then the mass must also change accordingly. It's a two-way street, a profound cosmic mirror, where cause and effect can be interchangeable. If this subtle, unsettling truth holds, then it hints at a universe where mass, the very substance of our being, and all that we perceive as real, is simply a projection caused by space curvature. Imagine for a moment shining a light at an object, say your hand, and watching its distinct shadow appear on the wall. The shadow, that two-dimensional outline, is a projection, an indirect manifestation, caused by the existence of your hand interacting with the light. Normally, in this simple, everyday analogy, you might be forgiven for confidently believing that we are the hand. It is our inherent mass that creates the subtle curvature of space around us that gives us weight and form. And yet, do we truly know that it doesn't work the other way around? Are we simply projections, intricate complex shadows, dancing on the wall of the universe, being brought into life and given apparent solidity by something more fundamental, going on in the subtle curvature of spacetime? And all the while, we're quietly going around living our lives, thinking that we are the fundamental thing, the solid, undeniable reality? We don't really know. Given that all you ever truly know is the reality you experience the world as it presents itself to your senses, it would be profoundly difficult for you to be able to tell the difference between these two scenarios. Both would feel equally real, equally immediate. But if relativity, that great cosmic teacher, has taught us anything, it is this: if there is no way of telling the difference between two situations, if the observable reality is identical, then we cannot completely dismiss the possibility that we are in fact in one scenario and not the other. Either that or the two might be far more intrinsically linked, more deeply intertwined than we ever thought possible. It is a profound, almost spiritual thought, inviting us to gently question the very bedrock of what we perceive as real. Of course, this is all just a theory, a beautiful mind-bending whisper from the edge of human understanding. There is no hard, irrefutable proof that Hawking radiation is even a real detectable thing. Although, as we gently explored, there have been some ingenious experiments that subtly hint that it might be. But this is just something interesting, something profound and humbling to quietly think about as you drift towards sleep. And even if it does one day prove to be the case, that our reality, our very being, is a projection, it's not going to affect your day very much. You will still think and feel. You will still experience the joy and sorrow, the warmth of human connection. And that in itself is more than enough reason for you to go about doing what you're currently doing, living your beautiful, complex life. But it is a powerful example of how, when we begin to gently examine the very fundamental building blocks of reality, when we explore the weird mind-bending warping effects of black holes, it can cause us to challenge our deepest, most ingrained assumptions about our very nature. After all, when you're quietly asking the profound question, "Am I real?" and the answer that whispers back from the cosmos is, "It's not certain," that's more than a little concerning, more than a little wondrous. Either way, black holes and their silent, powerful presence profoundly affect our reality, and they profoundly affect our universe. And not just because they seem to suck everything within their reach into them and famously give nothing back. They are, in a profound sense, the end, the final destruction to the ultimate cosmic sink of the universe. And yet, what if I were to whisper to you a truly startling possibility? What if I were to suggest that these cosmic devourers, these ultimate destroyers, might actually prove to be our salvation? What if black holes, in their bewildering complexity, might hold the key, the profound secret to traveling faster than the speed of light, defying what we thought were unbreakable cosmic laws? And what if they could even solve the energy crisis, providing limitless power in ways we couldn't have even imagined until recently, simply by messing with the fabric of reality itself? It's a thought that completely counters my expectations of physics, turning everything I thought I knew upside down. Perhaps, just perhaps, we have been thinking about black holes all wrong. To truly understand how a black hole, this ultimate cosmic anchor, might ignore the usual limitations on faster-than-light travel, and indeed, how it might do so in a way that you could hypothetically benefit from it, without having to plunge into a black hole's treacherous event horizon, and how it might produce near limitless energy at the same time, then we are going to have to understand more about the subtle, profound features of black holes than we've covered so far. It's a journey into the quiet intricacies of cosmic mechanics, revealing layers of complexity beneath their deceptive simplicity. It's actually quite difficult, in the grand scheme of cosmic understanding, to say much about the black hole's features at all, precisely because of that impenetrable veil, the event horizon. It is the ultimate information barrier, a boundary beyond which no light, no information, no whisper of detail can ever reach us. We simply cannot truly see what the inside of a black hole looks like. Its inner workings remain a profound mystery, a cosmic secret guarded by the laws of physics itself. In fact, in a concept known as the no-hair theorem, black holes are said to be almost devoid of any distinct features, much like a perfectly smooth, featureless head with nothing on it. They are the ultimate cosmic minimalists. The intrinsic features of a black hole are usually considered to be remarkably plain, remarkably simple. They have mass, they have charge, and they have angular momentum or spin. And that, in essence, is about it. You might quietly wonder, how do we even know these three fundamental things about black holes, given that no light can leave them to tell us about their nature? No signal can escape their gravitational embrace. The key to understanding these three subtle characteristics is that all three of them represent aspects of the black hole that can miraculously be felt and measured outside the black hole's event horizon. They are like the invisible currents in a deep ocean whose presence can be inferred from the ripples they create on the surface far above. Charge, for instance, behaves around a black hole in precisely the same familiar way it does around any other charged object we encounter in our everyday lives. That is to say, if a black hole possesses a net electric charge, then it will quietly, inexorably attract objects that carry a different opposite charge to it, and gently repel objects that share its charge. Think of it like a giant cosmic magnet, silently pushing and pulling on the charged particles and celestial bodies in the universe around it, its unseen influence stretching across the light years. Scientists can meticulously track objects that approach a black hole, observing their delicate dance, their subtle accelerations and decelerations. By carefully observing how quickly certain objects whose charge is known to us move towards or away from the black hole, scientists can gently yet precisely predict the hidden charge of the black hole itself. It's a silent conversation, a dialogue of forces revealing an unseen truth. Intertwined with this concept of charge, and perhaps even more fundamental, is mass. The immense mass of a black hole can also be profoundly felt outside the invisible sphere of its event horizon. In fact, it is the primary defining creator of the event horizon in the first place, the very force that sculpts the fabric of spacetime into that point of no return. This is because mass, as we understand it from Einstein's elegant insights, creates gravity, and it does so in a linear fashion, its influence diminishing, but never entirely vanishing with distance. This adherence to a predictable linear influence is in accordance with the same beautiful principles you might find in Gauss's law, a theorem about electromagnetism, but applied here to its gravitational analog. So it is profoundly possible to calculate the mass of a black hole by meticulously observing how far away objects are before they begin to subtly accelerate towards it, and then precisely how quickly they accelerate as they draw nearer. Of course, one needs to carefully factor in any existing charge at the same time, or your delicate results might get skewed, much like trying to weigh something on a scale that has a hidden magnet. This patient observation of cosmic dances allows us to infer the incredible unseen weight of these silent giants. Finally, we come to angular momentum, or spin. It is also possible with ingenious observation to detect the spin of a large mass object, even one as mysterious as a black hole. We are going to dive into the intricate how of this detection in just a bit, but for now, let us simply accept it as a given, a quiet truth revealed by the cosmic dance, and let us recognize as we contemplate these cosmic enigmas that black holes are most certainly very high-mass objects, their incredible density fueling their profound influence on the surrounding cosmos. It is this combination of mass potential charge and silent, ceaseless spin that defines their unique cosmic fingerprint, allowing us to categorize them even without seeing their true heart. Black holes exist in a truly astonishing spectrum of sizes, each a testament to the diverse and extreme conditions within our universe. The smallest known black holes, often referred to as microblack holes, are not merely small. They are almost impossibly tiny, yet they pack a punch of unimaginable density. These minuscule cosmic wonders have a mass comparable to that of our own moon, approximately 7.35 x 10^22 kilograms. Now imagine trying to fit all that lunar mass, the entire bulk of our familiar celestial neighbor, into a space that is just a mere 0.2 millimeters in diameter. thinner in size than a human hair. This incredible compression truly gives us a profound sense of how densely packed a black hole can be, a cosmic marvel that defies our everyday intuition of space and volume. Moving up the scale, we encounter stellar black holes, the remnants of those massive stars we discussed earlier. These are the workhorses of black hole formation, typically possessing a mass equal to about 10 times that of our Sun, and yet they compress all that stellar bulk into a diameter of merely 60 kilometers. To put that into perspective, imagine an entire city or even a small state crushed down to the size of a few football fields, yet containing the mass of 10 suns. The density is still mind-boggling, a silent testament to the extreme forces of gravity. Then there are intermediate black holes, a more recently confirmed category, quietly filling the gap between the stellar giants and the truly supermassive. These cosmic middleweights have the mass of approximately 1,000 suns, and they manage to fit all of that into a diameter of about 2,000 kilometers, still much smaller than our Earth, yet undeniably vast when compared to their stellar cousins. They are enigmatic, hinting at formation pathways, perhaps different from the simple stellar collapse, their existence still a quiet puzzle for astronomers to solve. But it is the largest black holes that truly dwarf us that stretch the very limits of our cosmic imagination. These are the supermassive black holes, the silent kings of the galaxies, with masses ranging between a staggering 100,000 to an unimaginable 10 billion times the mass of our Sun. Their sizes range from a mere 0.001 to a colossal 400 astronomical units AU. To grasp this, remember that 1 astronomical unit is the average distance from the Earth to the Sun, so a supermassive black hole can have an event horizon large enough to comfortably encompass the orbits of all the planets in our solar system with room to spare. They are the cosmic anchors, the gravitational hearts around which entire galaxies spin, silent, invisible maestros conducting a symphony of stars. Other than these 3 fundamental features, mass, charge, and angular momentum, there are, in theory, no other intrinsic differences between black holes. This is the essence of the no-hair theorem. Once a star collapses beyond its event horizon, all its complex features, its magnetic fields, its specific composition, its bumps and irregularities are smoothed away, leaving only these 3 fundamental properties. It's as if the universe, in its ultimate simplicity, strips away all extraneous details. If you could hypothetically put 2 black holes in the same cosmic room and ensure they had precisely the same mass, charge, and spin, it would be utterly impossible, theoretically, to tell them apart. They would be perfect cosmic twins, identical in every observable way. However, these 3 seemingly simple features are enough to have some incredibly profound and interesting effects on the vast area of space that surrounds a black hole, twisting and shaping reality in astonishing ways. Traveling inside a black hole, that ultimate cosmic journey, remains for all intents and purposes impossible, a one-way trip beyond the event horizon. Our familiar concepts of space and time break down past this boundary, dissolving into a realm beyond our current comprehension. But while the journey inward is shrouded in mystery, we do think we know a few things that must exist inside one, a whisper of understanding about the heart of darkness. Beating perhaps in the very heart of a black hole, there is thought to lie the singularity. In truth, this theoretical point actually is the black hole, the infinitely dense core. When we were discussing diameters earlier, remember that was merely the diameter of the event horizon, the point of no return. Again, we are not truly certain what the black hole, this singularity, actually looks like, because light can never escape it to bring us news. In a space that is theoretically infinitely small, a dimensionless point, all the immense mass of the black hole is packed, compressed to an infinite density. For the simplest models of black holes, the ones that do not spin, this singularity is envisioned as a single point, a dimensionless speck, where all reality collapses. However, in a rotating black hole, one that possesses that subtle angular momentum, The singularity is theorized to be more like a tiny, infinitely thin, spinning ring. This conceptual ring helps to define the spin for a point that otherwise has no volume, allowing for the mathematical description of its rotation. Our current physics, the very laws we rely upon, gets incredibly strange, almost fantastical around such a black hole. If one could hypothetically travel ideal paths, specific trajectories around this spinning ring singularity, it becomes mathematically possible to do some very strange things. Things that defy our everyday sense of causality, such as meeting up with your own past. This has deeply disturbing implications for our understanding of cause and effect, leading into classic time travel paradoxes, like the grandfather paradox, where one might prevent their own birth. Such paradoxes strongly suggest that our current ideas about singularities, particularly spinning ones, are not quite right yet, that there are still profound mysteries to unravel, elegant adjustments to be made to our cosmic map, because the singularity, if it exists, is so incredibly small, so compressed beyond all comprehension, it will likely take the successful merging of quantum theory and general relativity theory, two of the most profound yet stubbornly incompatible pillars of modern physics, to properly explain what is truly going on inside a black hole. And regrettably, we have not yet managed to achieve this grand unification. It remains the holy grail of modern physics. It may one day turn out that singularities, as we currently conceive them, do not exist in the hearts of black holes at all, perhaps replaced by some other equally mind-bending quantum phenomenon. But this is the extent of our quiet knowledge, so far the edge of our understanding, where speculation meets the profound unknown. Well, whatever it is that truly lies inside a black hole, whatever cosmic secret it holds in its infinitely dense heart, it is something that profoundly powers our hypothetical faster-than-light engine. This is because, like most other massive objects in the universe, it spins. And, oh, how it spins. This silent, ceaseless rotation of a black hole, a cosmic dance performed in solitude, creates astonishing effects in the space around it. Effects that might just be the key to bending the rules of the cosmos. As we gently travel out from the black hole's unseen center, we pass through the event horizon, that boundary of no return, often with surprisingly little fanfare. The event horizon itself, paradoxically, cannot actually be detected locally by someone crossing it. It's not a solid wall or a shimmering veil. It's a point where the geometry of space-time itself changes. Although a person safely outside the black hole might watch you slow down, appearing to come to a complete stop as you travel towards and then through it. From your perspective inside the event horizon, time would actually seem to flow normally. There would be no dramatic cosmic pause, no sudden jolt into timelessness from your immediate point of view. Normally, that is until the entire universe outside the black hole from your perspective runs its course in an instant, compressed into a fleeting moment, because time outside the black hole is traveling so incredibly fast compared to you. This is the profound essence of relativity, where perspective profoundly shapes reality. In fact, the only immediate local evidence you might have that you had passed the event horizon at all is because of something truly remarkable that exists just outside it, the photon sphere. In a remarkably thin, almost infinitely narrow zone just outside the event horizon, there exists a unique point in space. Here, if a photon, a tiny packet of light, enters it at precisely the right angle, it will enter a perfect stable orbit around the black hole. It's much like the way our moon perfectly orbits the Earth, held in a delicate gravitational balance. This infinitesimally thin zone is known as the photon sphere, a cosmic trap for light itself. And given the sheer unimaginable number of photons that have flown past black holes in all the millions and billions of years they have existed, it is quite possible that this sphere is perpetually filled with photons, a silent, swirling ring of light forever imprisoned just outside the event horizon. It is therefore quite possible that you would be instantly fried, vaporized in a flash of incandescent energy as you pass through this point, an intense cosmic microwave oven. However, it is just beyond this fiery sphere in a slightly less extreme, but still profoundly warped region that we find the zone that truly interests us for our purpose, the ergosphere. This is the extraordinary zone around a black hole, where we can most easily detect its incredible spin, its relentless angular momentum. And this is because in this zone, it is utterly impossible for us not to move. Stillness itself becomes an impossibility. You see, mass in its profound and ubiquitous presence throughout the cosmos affects space. We observe this elegantly in the curving effect of gravity on the travel of objects through that region of space like marbles rolling on a stretched fabric. However, it might be more accurate, more subtly precise to say that mass doesn't just curve space. It subtly drags on the space around it as it moves. Imagine a heavy rotating ball submerged in a thick viscous liquid. It doesn't just displace the liquid, but it subtly twists and pulls the liquid along with it, creating a slow, invisible whirlpool. When an object as unimaginably massive as a black hole spins, there is a profound, almost mystical effect, known as frame dragging. To put it simply, the very fabric of reality around the black hole begins to spin in a cosmic whirlpool, a silent, irresistible current that cannot be fought against. It's much like a real whirlpool in a river. Anything caught within its powerful embrace is spun around the black hole, not because it is being pushed by a direct force, but because the very frame of reference it sits in, the spacetime itself, is being subtly, profoundly pulled along. It's like standing on a moving walkway. Your own motion is amplified by the motion of the walkway beneath you. The greater the spin of the massive object, the faster this cosmic whirlpool churns. And in the ergosphere, this silent, irresistible rotation of spacetime can occur at a speed so incredibly fast that by the time you reach the event horizon, the space itself is actually moving faster than the speed of light. To stay at a relative standstill, from the point of view of an outside observer in this region, you would theoretically need to travel faster than the speed of light in the opposite direction, which, of course, as our familiar laws of physics tell us you simply cannot do. But isn't this, you might quietly wonder, fundamentally against the laws of physics? Doesn't Einstein, that great cosmic lawgiver, famously state that nothing can travel faster than the speed of light? The answer to that profound question is yes, indeed he does. But black holes, in their astonishing complexity, seem to have found an interesting, almost mischievous loophole in this seemingly ironclad cosmic rule. You see, Einstein's rule that nothing can travel faster than the speed of light only applies locally, right where you are in your immediate frame of reference. Within your own tiny bubble of reality, nothing can exceed the speed of light. But thanks to the profound insights of relativity, it is entirely possible for different frames of reference, different bubbles of reality, if you will, to move away from each other so incredibly fast that objects in them appear, from your point of view, to be breaking this light barrier. It's a truly weird, almost magical effect. But if you could somehow move next to them and enter their specific frame of reference, they would seem to subtly slow down and would once again start obeying the familiar laws of physics. It's a profound testament to the fluid relative nature of motion and the deep intricacies of spacetime. Frame dragging is not merely a theoretical construct. It is an actual measurable phenomenon, confirmed by precise astronomical observations. It is by meticulously measuring this subtle twisting of spacetime that scientists can learn the precise spin of a black hole, uncovering another layer of its hidden nature. However, according to a brilliant man named Roger Penrose, there may even be a way of exploiting this cosmic whirlpool, a clever trick to harness its immense energy. Imagine, if you will, sending a rocket into the section of the ergosphere, that spinning region of spacetime. As the rocket entered this cosmic whirlpool, it would be subtly yet powerfully sped up, its velocity increasing dramatically, due to being caught in the relentless current of reality itself. Once it had gained enough incredible speed, It could then theoretically fire a propellant in such a precise direction that it would push itself out of the whirlpool again like a pebble skillfully flung from a spinning top. But here's the magic: it would now be traveling at a much, much faster speed than when it entered, having gained energy from the very spin of spacetime. This ingenious method, gracefully named the Penrose process, could hypothetically net you energy equal to about 20% of the initial mass of your rocket. Now that might not sound like much at first, a mere 20%, but remember that profound truth revealed by Einstein's famous equation, E=mc2. Your 20% mass, no matter how small, would produce an amount of energy equal to itself multiplied by the speed of light squared, 299,792,458 meters per second squared. That, dear listener, is an utterly colossal amount of energy, a staggering, almost incomprehensible quantity. To harness this immense kinetic energy, this silent cosmic power, all you would theoretically need to do is travel to the nearest black hole, which is perhaps inconveniently roughly 3,000 light-years from us, and then gently enter its ergosphere with a rocket capable of surviving the intense gravitational forces and the dizzying frame dragging there. Ideally, you would need to find one that was not surrounded by a blazing accretion disk, because those infernal whirlpools of matter get up to temperatures of millions of degrees hot enough to melt solid rock into gas and then plasma. But you get the idea. Easy, right? Okay, perhaps this remains a little impractical for us for now. The engineering challenges are, to put it mildly, immense, and the distances are vast. But the profound implications for faster-than-light travel that black holes subtly demonstrate through frame dragging might just offer us the key, a profound glimpse into one day truly beating the light barrier for real. Not by attempting to go faster than light ourselves directly, but by somehow cleverly convincing the very frame of reference we are in to travel at those faster-than-light speeds, just like the spacetime around a spinning black hole does. It's a subtle shift in perspective, but one with monumental consequences for our future in the stars. Of course, if this incredible feat requires the immense energy of a black hole to accomplish, we might be out of luck for now, confined to our slower familiar speeds. But it is an incredible glimpse into what is possible, a silent whisper from the cosmos about pathways yet undiscovered. And indeed, scientists are already quietly looking into the profound power of frame dragging for future travel concepts, for bending the rules of the universe in ways that seemed purely fantastical just a few decades ago. But perhaps that's a topic for another time, another quiet evening of cosmic contemplation. Either way, this all just highlights once again how our universe truly is very different, very much stranger than what we might have ever imagined in our wildest dreams. The gentle hum of its mysteries continues to unfold, beckoning us to wonder. And here's another surprising thing about black holes. A quiet paradox that might reshape your understanding of these ultimate cosmic devourers. Falling into a black hole is strangely a lot harder than it sounds. You might expect it to be relatively easy, almost like slipping down a well. After all, aren't these the ultimate absorbers? Quite literally the largest sources of gravity out there, drawing everything to them with an insatiable pull. Shouldn't it be easier then to fall into them than into any other thing in the universe? You might have intuitively thought so, but paradoxically, your intuition is gently, subtly wrong. These galactic maws are surprisingly one of the hardest places in the universe to actually get inside. So much so that during his lifetime, even Einstein, with all his profound insights, believed you couldn't get inside them at all, that the process would take an infinite amount of time. And not only that, but these bewildering black holes might even remarkably eject you away from them at speeds astonishingly close to the speed of light, like a cosmic slingshot. Shouldn't it be then that these objects with their immense gravity would be incredibly easy to get into, like a slide that gets steeper and steeper? The further along it you go, you might instinctively expect to speed up more and more, accelerating relentlessly the closer you get to the black hole's silent center. However, while this is right, you do speed up so much so that your velocity will begin to profoundly approach the speed of light. It is also, in a deeper sense, wrong. In almost all cosmic circumstances, you will not find yourself simply plummeting directly towards the center of the black hole. And this isn't me talking about some strange quirk of time or relativity, some subtle optical illusion. This is something that would be truly observable from whatever frame of reference you're watching, from a tangible physical reality. Confused? Don't worry. Allow me to gently explain this profound paradox through the real-world example of something called an accretion disk, those fiery halos that often betray a black hole's presence. Black holes are at their very heart profoundly simple objects, almost minimalist in their cosmic design. In something known as the no-hair theorem, black holes are said to be devoid of almost any distinctive feature, just like a perfectly smooth, featureless head with nothing on it. The intrinsic features of a black hole are, as we explored, usually fairly plain too. They have charge mass and spin, and that's about it. As such, accretion disks are not actually a necessary part of black holes. A black hole can exist perfectly fine without one sitting there dark and unobservable, drifting silently through the emptiness of space. However, when a mass such as an unlucky star or a vast cloud of gas strays too close to the black hole's overwhelming gravitational pull, it can be gently yet powerfully torn apart by the vast tidal forces at work. The star is stretched into a spaghetti-like strand, its material then drawn towards the black hole's insatiable center. Strangely enough, though, this matter does not all immediately fall into the black hole's event horizon. Instead, the matter usually coalesces into a sort of flat swirling ring, a cosmic disk of superheated gas and dust that orbits gracefully yet furiously around the black hole just outside its event horizon. While eventually, inexorably, it does all enter this process, can take an unimaginably long time. Some accretion disks can take hundreds of millions, even 1,000 million years to be completely absorbed, a cosmic slow-motion feast. So what exactly is going on here? Why does the matter not simply immediately plunge into the black hole, drawn by its overwhelming gravity? The answer is that it comes up against a surprising and profoundly important principle of physics, one that quietly governs all motion in the universe, the conservation of momentum. This idea, first described with elegant simplicity by the mathematician John Wallis in 1670, and then brilliantly pioneered by his contemporary Isaac Newton, a decade or so later, asserts a fundamental truth. If you have a group of objects, the total motion of those objects, their collective momentum, must always remain precisely the same unless an external force acts upon them. Imagine for a moment a simple collision. If one particle with a certain momentum gently bumps into a second particle that is standing perfectly still, and both then bounce away from each other, the total amount of motion for the two particles, when added together, must precisely equal the amount of motion of the first particle on its own before the collision. No momentum can be lost. It is simply transferred. Or consider a rocket on a launch pad initially with zero momentum, perfectly still. It can only give itself momentum, begin to move by firing a propellant in the opposite direction. Once you carefully add up the amount of momentum imparted to the air by the propellant going down and the amount of momentum given to the rocket by going up, then the upward momentum and the downward momentum are exactly equal, resulting in the same net zero momentum you had to start with. It's a beautifully balanced cosmic equation. This concept might at first glance fall a little outside our everyday expectations. After all, we as humans often stop and start walking around, seemingly without consciously obeying this profound law. However, if you carefully evaluate all the particles involved, your body, the floor beneath you, the earth itself, this law is always perfectly kept. You would struggle to move anywhere to gain any momentum without a floor or ground to push against. The momentum you impart to the floor by pushing off it must precisely equal the amount of momentum imparted to you, but in the opposite direction. You just don't notice it because the floor is so immensely massive compared to you. The minuscule amount of momentum you give to it does not move it in any noticeable way. It's a silent, constant exchange of forces upholding the delicate balance of motion. But what you might gently wonder, has this profound principle of conservation of momentum got to do with the challenge of falling into a black hole? Well, consider this next elegant example, this time to do with angular momentum. The momentum of rotation. Imagine a graceful ballerina standing on a single point, her arms outstretched, spinning slowly. The particles in her hands have a certain momentum. They are moving a certain distance around the central axis in a certain amount of time. However, when she tucks her arms gracefully close to her body, what happens? Well, she suddenly begins to spin much, much faster, a blur of motion. This is a classic and beautiful example of momentum trying to be conserved. You see, the momentum that was present in her outstretched hands is still trying to travel at the same speed it was previously traveling at. However, suddenly, because her hands are now tucked close to her body, they are traveling a much smaller distance to complete one revolution. And because they are trying to maintain their initial speed and now have much less distance to travel to complete one full turn, they effectively complete that revolution much, much faster. This causes the ballerina herself to spin faster when she tucks her hands in and slower when she stretches her hands out again, a graceful demonstration of a fundamental cosmic law. Now imagine this principle applied on a vast cosmic scale to matter swirling around a black hole. In most scenarios, matter does not fall in a perfectly straight line directly towards a black hole like a stone dropped down a well. Almost always it will slightly miss the black hole, and instead it will begin spiraling inward towards its silent, powerful center. As it gets caught in the black hole's immense gravity, this matter now possesses angular momentum. It's spinning as it falls. And just like our ballerina, as this matter gets closer and closer towards the center of the black hole, it starts speeding up, moving at an ever-increasing velocity on a smaller and smaller orbit. It gains more and more angular spin, rotating faster and faster the further down the gravitational well it falls. However, unlike the ballerina, this matter has an ultimate unyielding speed limit. To contend with the speed of light, nothing in the universe as discovered and articulated by Einstein can travel faster than the speed of light. This is an unbreakable law, a fundamental constant of the cosmos. So what happens to our spinning, furiously accelerating matter as it falls further and further into the black hole's gravitational embrace? Due to the massive, incomprehensible forces at play and the extreme curvature of spacetime involved, it eventually reaches a point where it simply can't go any faster. It's hit a cosmic roadblock, an absolute limit. And because it cannot spin any faster, it profoundly cannot fall any further into the black hole. The conservation of angular momentum locks it into orbit. This inability to fall further, this cosmic roadblock, has several astonishing effects. To begin with, as you can imagine, it creates immense friction. All of this matter furiously spinning at such blistering speeds around the very edge of the event horizon begins to constantly bump and grind into each other. And when this violent bumping and grinding is taking place at near-light speeds, things get unimaginably hot. The matter in a black hole's accretion disk can reach temperatures up to 10 million Kelvin, far hotter than the surface of our sun. This infernal heat is enough to melt anything down to a superheated plasma, a glowing ionized gas. These constant violent collisions among the particles pummel all the atoms involved, squeezing them, causing them to give off more and more of this immense energy, much like squeezing a lemon to extract its juice. Between 10% and 40% of an atom's original mass is given off this way, transmuted into pure energy, which then radiates out across the universe in a blinding display. For a point of comparison, consider nuclear fusion, the very process taking place in the heart of our sun. That process converts only about 0.0% of mass into energy. Let that astounding difference quietly sink in for a moment. Consider how incredibly bright and powerful the sun is at a mere 0.7% efficiency. How bright, then, can a black hole's accretion disk get? The brightest such disks are known as quasars, and they can reach brightnesses that stagger the imagination, exceeding 1,000 times the total brightness of every single star in the Milky Way galaxy combined. Imagine looking at our entire galaxy with its hundreds of billions of stars and then multiplying that light by 1,000. That is the sheer overwhelming luminosity of a quasar, a cosmic beacon powered by matter reluctantly falling into a black hole. The good news for the matter trapped in this cosmic whirlpool is that additionally, some of that angular momentum, that ceaseless spin, starts to be shed with the departing energy radiating away into space. More momentum gets shed by imparting it to matter further up and out of the accretion disk as faster moving particles in the inner regions knock into slower particles moving just above them, giving them an extra push and slowing down the lower, more tightly bound particles. In this elegant, indirect way, matter slowly begins to lose its excess angular momentum, its frenzied spin, and begins to finally gradually fall into the black hole itself. Even more momentum can be shed through one of the most striking and mysterious features of quasars and black holes, their powerful jets. We do not understand everything about these colossal jets, precisely how they form what they are comprised of, or why only a small fraction of black holes with accretion disks possess them. But current theories suggest they are caused by incredibly powerful magnetic forces that are created by the violently spinning accretion disk itself, or even by the immense rotational power of the black hole itself, its silent spin acting like a cosmic dynamo. These forces somehow draw up material from the inner regions of the accretion disk and fire them out into space at astonishing velocities, creating colossal fiery plumes. It's likely that as the accretion disk spins, its superheated electrically charged plasma creates immense magnetic fields in keeping with Ampere's law, which states that moving electric charges create magnetic fields. The power and specific shape of these fields are such that there is only a narrow funnel-like channel at the north and south poles of the black hole for particles to escape. These magnetic fields may work in a similar way to the rifling inside a gun barrel, channeling and accelerating particles down a narrow energetic path. Particles caught within these powerful magnetic channels are then accelerated to near relativistic speeds, given only one direction they can go. Even though we don't quite know yet why they go, perhaps they are like the intense steam of a kettle fired out through the only gap that exists in the face of this incredible gravitational and heat pressure, and when they go, they truly go. These relativistic jets travel further than the galaxies they originate from, often stretching for millions, if not billions of light years across the cosmic void. One such jet, with its rather catchy but technical name, has its X-rays reaching Earth from a staggering 12.7 billion light-years away, albeit faintly. This is because the radiation produced by such jets is very tightly focused in one direction, much like a laser beam, an effect known as relativistic beaming, or the lighthouse effect. When the beam is pointed away from us, it is much harder to see, making these distant cosmic lighthouses elusive, unless they happen to be pointing their silent gaze directly our way. It's profoundly worth noting again that this immense energy and matter expelled in the jets does not come from the black hole directly. Remember, nothing can escape from inside a black hole. Instead, the matter and radiation that comprise these jets come from the intensely energetic accretion disk surrounding the black hole, which is fueled by matter falling towards the black hole but not yet into it. And again, a lot about these jets is still theoretical, a quiet whisper of scientific understanding. We can see them, even observe them moving and changing over time, but we don't fully understand their intricate mechanisms or what causes them to burst forth with such incredible power. Our current understanding of accretion disks does not even fully explain how the conservation of momentum is entirely kept. There is still some quiet mystery about where all that excess momentum ultimately goes. But the sheer power at play in these phenomena is undeniable. Einstein may have been wrong in his initial belief that it was impossible to fall into a black hole. It evidently is possible, albeit a long, convoluted process involving the shedding of angular momentum. But when some black holes are firing material away from them at near relativistic speeds for distances spanning entire galaxies, well, it's evidently possible to not fall into them too, to be flung away with incredible force. And once you factor in the immense outward pushing force of matter that is millions of degrees hot, furiously attempting to shed its own momentum, perhaps you wouldn't want to get too close to one anyway. The universe, in its quiet wisdom, provides its own deterrence to the most extreme cosmic phenomena, so we've journeyed together quietly observing how the awe-inspiring effects of a black hole can span entire galaxies, influencing their very structure and dynamics. But this inevitably begs a profound and simple question. How big can a black hole actually get? What is the ultimate size limit for these cosmic devourers? Finding the largest black holes is perhaps surprisingly not always difficult. All you generally need to do is look directly at the very center of large galaxies. These are the supermassive black holes, the silent gravitational anchors around which entire galactic empires gently swirl. They have grown steadily since their formation. Billions of years ago, silently accreting more and more matter, continually increasing their immense mass. The very largest of these supermassive black holes can be billions of times the mass of our own sun, truly colossal entities, beyond our easy comprehension. However, it may come as a quiet surprise to you to realize that some of the most massive black holes we know of are actually paradoxically the youngest. This seems to defy our intuition, doesn't it? After all, shouldn't the oldest black holes have had the most time to grow, to devour more matter? You see, when we look at distant galaxies across the vast cosmic ocean, we are not just looking across space, we are also looking back in time. The light from galaxies billions of light years away has taken billions of years to reach us, meaning we are observing them as they were billions of years ago in the universe's distant past. The galaxies we see, for instance, at 10 or 11 billion light years away, are light that left when the universe was only 2.8 or 3.8 billion years old. From our perspective, these are still relatively young galaxies. Surely, though, it should be the case that nearer and thus older, supermassive black holes in our cosmic neighborhood are more massive, seeing as they've had so much extra time, billions of years, to patiently consume matter falling into them. So what exactly is going on here? Why does this quiet paradox exist? The very largest supermassive black hole we know of, a true cosmic behemoth, is known as TON 618. It boasts an incredible, almost incomprehensible mass of 66 billion solar masses. By itself, its sheer mass is comparable to that of an entire large galaxy, a truly staggering figure. However, TON 618 is exceptionally far away from us, its ancient light taking a colossal 10.8 billion years to reach our telescopes. This means we are observing it as it was 10.8 billion years ago, when the universe was just a mere 2.8 billion years old. This makes it, from our perspective, a very young black hole in a very young galaxy. By comparison, our own Milky Way galaxy, our cosmic home, is approximately 13.6 billion years old, a truly ancient spiral. Yet the supermassive black hole found at our galaxy's core, known as Sagittarius A, is only a comparatively modest 4 million solar masses. The Andromeda Galaxy's supermassive black hole, while larger than ours, is still only a mere 200 million solar masses. There is a profound discrepancy, a quiet puzzle between the age and the observed mass of these cosmic giants. One of the big factors to consider here is the inherent difficulty in detecting and accurately measuring black holes. This is still a really new field of research, a frontier of exploration, as technology has only just allowed us to begin truly observing black holes in the last few decades. Even then, we can often only observe the area surrounding black holes. That is the luminous accretion disks that exist before the event horizon. Telescopes, like the Event Horizon Telescope, a marvel of human ingenuity, take immense amounts of time and data to image just one black hole. So our general understanding really is still quite limited, a faint sketch of a grand design. In fact, most of the distant black holes we know about can only be seen because they are quasars. Ton 618. That colossal distant giant is a quasar. This means that matter is pouring into the black hole's accretion disk at an incredible, almost unceasing rate. And because of this rapid infall, it has erupted into a quasar, a blinding beacon of cosmic light. Quasars, those luminous wonders, can only be sustained as long as matter is continuously falling into them. Otherwise, they quietly revert back to dark, silent black holes, their brilliance fading into the background. It's hard to fully grasp the physics of the accretion disk in such extreme environments, but it is widely believed that the friction and heating here are so incredibly great that the accretion disk of a quasar by itself can produce thousands of times more light than entire galaxies combined. Ton 618. That distant monster produces as much light as 140 trillion suns, utterly outshining the galaxy it resides in, to the point that we can't even see the galaxy from our perspective. It is lost in the brilliant glare of its central engine. However, because quasars are the brightest objects in the universe, they can be seen from incredibly far away, acting as cosmic lighthouses across billions of light years. So one profound reason for the apparent prevalence of very large black holes being so far away, appearing to us as younger entities in the early universe, comes down to something known as Malmquist bias. This is a subtle statistical effect in astronomy, where brighter objects, even if they are further away, appear more plentiful in our observations. In reality, we simply cannot see the dimmer objects at those immense distances. It's like trying to survey all the lighthouses in the world from a single viewpoint. You'll mostly see the brightest ones, even if there are many dimmer ones closer by, but obscured by fog or distance. This implies there may be a compelling argument that the largest supermassive black holes are actually distributed fairly evenly throughout the universe. But our observational window simply favors the most luminous ones in the distant past. If a galaxy harbors a very large black hole, but it's not currently acting as a quasar, it means we won't be able to see it beyond a certain distance, because the galaxy itself is much, much dimmer than a quasar, blending into the cosmic background. Another profound reason why we don't observe the very biggest black holes close to us in our local cosmic neighborhood is intimately tied to the very nature of the universe itself and its grand unfolding story. Shortly after the Big Bang, as you may quietly know, the universe began an eternal journey of expansion, ceaselessly growing larger and larger. And during the early universe, matter was far more densely packed together, far closer to its cosmic neighbors. This denser environment meant that quasars were much more common back then, their blinding brilliance fueled by an abundance of raw material. Quasars, remember, need extreme amounts of matter continuously falling into them to give off their prodigious light. And in the bustling, crowded early stages of the universe, there was simply a lot more gas around raw material, ready to be consumed. Not only has the universe expanded, spreading its contents thinner, but over vast cosmic timescales, that primordial gas, the very fuel for stars and black holes, has been gradually converted into stars themselves. And as we gently explored earlier, some of the largest types of these stars eventually live out their dramatic lives and turn into neutron stars and black holes themselves, meaning that this gas never gets recycled back into its raw gaseous form to feed future quasars. Less available gas in the cosmic larder means less gas will fall into a supermassive black hole, leading to fewer active brilliant quasars in the later, more sedate universe. One of the prevailing theories for the ultimate fate of the universe is actually based on this very process, a concept known as the Big Freeze. This melancholic, yet scientifically compelling idea suggests that after some trillions of years, all the remaining gas in the universe will eventually be converted into stars, which will then burn out. leaving behind only the cold remnants of stellar corpses and black holes. Even now, we quietly observe some galaxies where their gas has been completely used up, meaning no new stars can form within them. These are often called elliptical galaxies, vast, quiet, cosmic cities that have used up all their building materials. In contrast, spiral galaxies like our own Milky Way still retain structures of gas and dust, and thus can still produce new stars quietly continuing their cycle of creation. It is interesting and a quiet confirmation of these ideas that most of the largest supermassive black holes appear to reside in elliptical galaxies, those ancient cosmic cities where there is no gas left. This suggests a profound connection gas needs to lose its angular momentum, its spin, to fall into the galaxy's central supermassive black hole. And if that has happened, if vast amounts of gas have already lost their momentum and fallen into the core, then the supermassive black hole at its heart is likely to be much, much bigger, having gorged itself on all that infalling matter. With elliptical galaxies, this process of gas consumption and black hole growth has already largely occurred, whereas with spiral galaxies, this hasn't happened to the same extent, perhaps due to ongoing star formation that uses up the gas or dynamic processes that prevent it from reaching the core. One such trigger for gas losing its angular momentum for its cosmic spin to dissipate could be the powerful gravitational influence of nearby galaxies, or even dramatic cataclysmic collisions with other galaxies. These immense cosmic encounters can disrupt stable gas clouds, stripping them of their angular momentum and funneling them towards the galactic center, fueling the growth of the central black hole. In addition, as we noted, there is simply less raw gas available in the universe now than there was during the early universe. So black hole growth probably occurred much more rapidly then in the tumultuous youth of the cosmos, but has slowed down considerably now in the universe's more mature, spread-out phase. This might be why there is no active quasar within 500 million light-years of us. As the universe ages and things become less chaotic and more spread out, the number of active quasars has gradually decreased, which means the only quasars we currently see, some of which are the largest black holes we know of, are the ones that burst forth with their immense brilliance a very long time ago, their light only just reaching us now. So to return to our quiet paradox, why are the largest supermassive black holes often the youngest from our perspective? Well, although it may appear that way, it might not actually be the case at all. We can measure distant bright quasars simply because we can see them. Their immense luminosity makes them visible across billions of light-years. Older and closer black holes closer to our own cosmic time may also be equally large, if not larger. But because of Malmquist bias, because they are no longer actively consuming vast amounts of matter, and thus not shining as quasars, we simply haven't found them yet. As dedicated studies continue, and our technological eyes improve, we will slowly, patiently start to get a more complete and nuanced picture of the universe around us, filling in the missing pieces of this grand cosmic puzzle. So there we have it. Ear listener, we have journeyed together through the silent, profound mysteries of black holes, exploring almost everything you could want to know about them, from their dramatic births to their potential distant evaporations, from their strange effect on time to their astonishingly practical, if hypothetical implications, for faster-than-light travel. Is there more to be discovered about them? Almost certainly. The universe is an unending book of secrets, and black holes are but a single, albeit profound, chapter. But one thing is for sure, they have completely distorted my concept of what is normal in this universe of ours, stretching the very boundaries of what I thought possible. They are the ultimate testament to the universe's boundless capacity for wonder, for paradox, and for beauty. If you found a quiet value in this journey, in this gentle exploration of cosmic mysteries, be sure to follow along for more amazing space content, more whispers from the cosmos. But for now, as the night deepens and the stars gently begin their silent dance above, I am Alex McColgan, And this has been Astrum. All the best, and may your dreams be filled with quiet wonder and boundless curiosity. The universe, in its quiet and enduring existence, continues to present us with profound mysteries, and among them, the ultimate fate of black holes remains a subject of deep contemplation. We've explored how they form, how they influence spacetime, and even how they might slowly evaporate through Hawking radiation. But as we look across the vast cosmic distances, we see evidence that challenges our simple notions of growth and age. The fact that the largest supermassive black holes appear to be the youngest is a puzzle that invites us to delve deeper into the universe's early, more turbulent history. This apparent paradox, where distant ancient black holes seem vastly more massive than their closer, seemingly older counterparts, is partly a trick of cosmic light. The Malmquist bias gently reminds us that our telescopes are in essence cosmic lighthouses, best at spotting the brightest beacons across unimaginable distances. In the universe's youth, conditions were ripe for these cosmic engines to roar to life. Shortly after the Big Bang, the cosmos was a much denser, more chaotic place. Imagine a vast, swirling cloud of primordial gas, far more concentrated than it is today. This abundance of raw material was the perfect fuel for nascent, supermassive black holes to grow rapidly, gorging themselves on the surrounding gas and dust. These early voracious feeders became the blindingly luminous quasars we now observe billions of light years away. A quasar is, in essence, a supermassive black hole in its most active, most brilliantly destructive feeding frenzy. The immense friction and energy released as vast quantities of gas spiraled into their accretion disks created light that outshone entire galaxies, making them visible across the vast expanding universe. Ton Cygnus 18, our record-holding giant, is a prime example of such a phenomenon. A blazing monument to a time when the universe was young, turbulent, and abundant with the raw materials for rapid growth. As the universe matured, its fundamental nature began to shift. The ceaseless expansion, a gentle, relentless stretching of space-time, caused matter to become more diffuse, more spread out. The dense clouds of gas that once fueled quasars began to thin, slowly transforming into stars, which eventually consumed their hydrogen fuel, and in many cases, condensed into neutron stars or other black holes, never to return to the gaseous form. This transformation meant that the era of rampant quasar activity, the period of most dramatic black hole growth, gradually waned. This is why in our local cosmic neighborhood, within say 500 million light-years, we find no active quasars. The conditions that allowed for such explosive growth simply no longer exist with the same frequency. We see this evolution vividly in the different types of galaxies that populate our universe. Elliptical galaxies, often found to harbor the most massive black holes, are like ancient cosmic cities that have used up all their building materials. Their gas and dust, once plentiful, have largely been converted into stars or have funneled into the central supermassive black hole. The absence of remaining gas suggests a history where immense amounts of matter have already fallen into the core, allowing the central black hole to grow to colossal proportions. In contrast, spiral galaxies like our own still retain their dusty arms, quietly forming new stars and preserving a more complex balance of gas dust and stellar populations. This ongoing star formation may prevent vast amounts of gas from reaching the galactic center, thus limiting the growth of their central black holes compared to their elliptical cousins. The quiet influence of galactic interactions and collisions with other galaxies also plays a profound role. These cosmic fender benders can strip gas from its stable orbits, causing it to lose its angular momentum and funneling it directly towards the galactic core, initiating new bursts of quasar activity and fueling rapid black hole growth. This suggests that the immense size of some distant black holes might not solely be due to their early start, but also to a more frequent occurrence of such violent galactic mergers in the universe's chaotic youth. So while it appears that the largest supermassive black holes are often the youngest in our observational window, this might simply be a profound trick of perspective, a limitation of our current cosmic vision. We can detect distant ancient quasars because they are unbelievably bright cosmic fireworks that illuminate the early universe. But there could very well be older, equally massive black holes closer to us that are no longer actively feeding, and thus remain dark and elusive, hidden by their very stillness. As our studies continue, as our technology improves patiently, refining our ability to observe these silent giants, we will undoubtedly begin to uncover a more complete and nuanced picture of their distribution and evolution throughout the universe. And so our journey through the enigmatic world of black holes draws to a close, at least for tonight. We've touched upon their terrifying power, their mind-bending effects on space and time, their strange and beautiful mechanisms of formation and growth, and even the perplexing idea of their slow, quiet evaporation. We've explored the whispers of quantum fields and the profound implications of relativity, stretching our minds to grasp concepts that defy our everyday experience. Is there more to be discovered about them? Almost certainly. The universe is an endless wellspring of wonder, and black holes are but one fascinating, deeply complex facet of its grand design. But one thing is for sure, they have profoundly stretched our understanding of what is normal in this universe of ours, pushing the boundaries of possibility and challenging our deepest assumptions about reality itself. They are the ultimate cosmic teachers, silently revealing the universe's most extreme truths. They show us that space and time are not fixed, but fluid, bendable fabrics. They hint that nothing is not truly empty, but a bustling quantum foam. They suggest that cause and effect might be more intertwined than we ever dared to imagine. And they whisper of potential pathways to incredible energy and unimaginable journeys, even as they remain the most formidable devourers in the cosmos. As you drift towards sleep, may these gentle whispers of the universe, these profound ideas about black holes, settle softly in your mind. May they inspire a quiet sense of wonder, a gentle curiosity that continues to seek out the unknown, even in the deepest darkness. For in the heart of these cosmic enigmas, we find not just destruction, but also profound beauty, limitless energy, and perhaps the very keys to understanding our place in this vast, mysterious, and endlessly fascinating universe.